Presents our first webinar for 2022. So we have today two very interesting topics, right? We're going to first talk about some research that we recently published on natural language processing, so FinEAS, financial embedding analysis of sentiment. It's gonna invest like 30 minutes, so it's gonna be a short presentation. We think the format of having short presentations it's some sort of a better one. And then we have with us Professor Matthew Dixon, who's going to talk us about Bayesian reinforcement learning for wealth management. Really two very interesting topics. So let's get started, right? Okay, just a sec. Let me share again because I'm more used to. Okay, good. Okay, so first a little bit of introduction of our institute. So we actually launched the institute already 3 years ago. The idea of the Artificial Intelligence Finance Institute is to provide education and research for AI. AI. Can you guys hear me well? That I'm seeing some. Can you guys hear me well?
I can hear you well, Miquel.
Yeah, perfect. Okay, so the idea about the creation of the institute was again to provide top research and training for financial professionals, computer scientists, quants that want to use and want to investigate how they can incorporate AI, machine learning, in addition to other quant modeling tools, right? So so we offer a couple of boot camps every year, right? Last year we actually offer more than that, but we have soon our winter boot camp 2022 from 10 days. It's online, right? We offer in-person courses, but obviously the pandemic has changed a little bit that, and we offer a 10 days program from February 21st to March 4th, 2022. So in a month and a half. And here we provide 40 hours of lectures, practice, speakers. We have a really fantastic faculty with Matthew Dixon, with Peter Colm, with Marcos Lopez de Prado, with Miki Atbal, with Tim Leung, with Stefan Jansen, and many other very interesting speakers. So we think it's a good opportunity to some sort of learn from firsthand from best practitioners and academics on AI, how to use artificial intelligence, machine learning in finance. So obviously this is very exciting because we have completely new fields, right? So we have the use, so we investigate and teach the use of deep learning, reinforcement learning, and natural language processing. Okay, so that was a little bit of a commercial. So now let's get started, right? So I'm gonna be talking for 25 minutes on natural language processing, on how we can use natural language processing in finance. So we're gonna be seeing. Well, I'm going to be presenting a model that we launched on November 2021, and I'll first give some sort of for the ones that maybe haven't seen natural language processing and natural language processing and finance, a short intro, just to give you a sense of what are the main tools and techniques I'm using, and then I'll introduce quickly our paper. So the idea of using natural language processing in finance, right? We'll see a sentiment application. It's obviously very appealing because finance is a information processing game. So we have lots of news, lots of text, audios, and so on. So the idea is how we can use machine learning AI, right, to some sort of extract value for, in that particular case that we will be investigating for investing purposes. But, and the first thing we always say is that we follow the same, some sort of machine learning modeling steps and framework. It's about having a data set. It's about feature extraction and scaling, feature selection, obviously sampling. I'm going to be talking about sampling today a lot because of we need, obviously, if we want our language model to be good, right, we need to make sure that our data set is also good. So I'm going to be talking about a little later on about that. So pre-processing is a crucial step, right? Making sure that you have a rich, diverse, representative, and so on data set, right? These data sets are very large, as we will see, right? This is a little bit misleading. The fact that that NLP models some sort of use so much data, because actually a lot of data is repetition. So if you look at news, so there are lots of news that talk about the same thing, so to speak, right? So that can be misleading. You might think that you're actually processing lots of interesting things, and it's not the case. Anyway, so we have to do with the pre-processing, the learning, evaluation of language models. This is also a tricky topic, right? So how can we measure the success of these models, and obviously prediction? Then we will use these models with real data. Okay, so this is a workflow, and I'm going to go through all the steps. But the first thing is we need to do the data extraction. In our paper, we didn't do all this data extraction because we actually used a very good data set provided by Ravenpack. So we had, but if you some sort of start from scratch, right? So you obviously oftentimes need to do web scraping, which is in itself a very interesting topic, and so on. So data extraction, it's a big issue, right? For the ones who've been doing, so it's these are largely dimensional data sets. You need to take care of lots of issues that arise. There are pictures, there are tables, and so on and so forth. So data extraction we're going to be focusing, or I'm going to be focusing my talk on the NLP models that can be used for that. And I'll say just a couple of things here, right? Whenever we try to measure sentiment, which is which I'm going to be talking about, we basically have some sort of two ways to do it, right? So one way to do it, it's this point number 6 that we see here in the slides are frequency-based methods. So we count the number of positive words, we count the number of negative words, and use that as a feature, right? To then use our models to say, okay, so if they have this number of words versus the number of negative words, then this implies positive sentiment, negative sentiment, and so on. But I'll be focusing my talk on deep learning models, right? So because deep learning models, so since right, so the best NLP models these days, right? At least the ones that are published and the ones that the best state-of-the-art performance are the ones that use deep learning. So I'm going to be discussing again a model that we recently launched. And this can be used in a variety of contexts, right? But I'll begin talking about sentiment. The evolution of these models, right, started from using lexicon methods, which are what I said a moment ago, which is using frequency methods, right? So you have number of words, number of positive words, number of negative words. You create a dictionary, for example, look at McDonald's, which has some sort of positive words, negative words, and these models are pretty good, right? But we can see here in a specific application using the financial phrase bank, which is a pretty popular, right, data set for financial sentiment, right? You can achieve a 61% accuracy, which is good, right? But after that, so there are two evolutions, right? One is embedding, so the fact that instead of words being sort of every word being one dimension, so to speak, every word being for example, using one whole encoding. So every word in itself is a feature. So we have lots of dimensions, maybe 50,000, and one single layer, right? And that brought 78% accuracy. But then, right, the NLP researchers brought to the table with word2vec in 2013, right? So a new way to do things. And this new way to do things was now words have multiple dimensions, right? For example, globally, words have 300 dimensions. And then also, then this is a better way to represent words, right? And second, the words have different meanings in different contexts, so context is incredibly important, right? So RNNs, so recurrent neural networks, on LSTMs were the thing that was that brought the next step, so to speak. So now we're using multiple layers, and accuracies are much higher when using deep learning models. So I'll discuss also these numbers, but also obviously a few caveats that arise. Okay, so language models are basically predicting words in a context, right? So the best thing that, or many of the language models were, okay, so let's try to see what is next word. So can I fill the next words? The students open there, right? And there are some options, right? So we have to compute P of xt plus 1 conditioned to the other words that are in the sentence, xt, xt minus 1 to xt, right? So this is the idea. So obviously this is a super largely dimensional problem, and the n-gram models was some sort of the first idea that was used, but still there's still the cost of dimensionality was a limitation to these models. You have zillions of parameters, right? And these models work not really very well. So what the new era, right, of language models was the neural language era. So it comes again in two steps. One is to solve the cost of dimensionality in terms of using word vectors, right? So Benjo et al. And Vincent and Jovan started to talk about how we can some sort of make a better representation of the words, right? And the second thing is how we can understand the context and the ordering of the words, right? So recurrent neural networks, and after that, right, LSTMs that provide it, and these days transformers, right, are the tools that help to deal with these vectors of this word embedding, so to speak, or word2vec. So every word now is going to have, instead of 50,000, a vector of 50,000, one hot, right, very sparse vector, a vector of maybe 300, Groby has 300, and you have, right, linguistics, for example, has this representation, right? So the idea was brought by Miquel et al., and they invented word2vec, right? Not discussing here in depth, but the idea is, right, to some sort of compute these or estimate these vectors in regards to the position that a word has in a sentence, right? So here we have, this is the objective function. So we have to maximize the predictive accuracy, and we compute. So these vectors of 300 entries, so to speak, or whatever number you think is going to help you to solve the problem, right? And so was the first solution, or one of the best solutions invented, right? So now these days, so you can also obviously, right, compute your own embeddings. So you can go to TensorFlow and actually, train your own embeddings, right? So, and this is obviously very useful because maybe, for example, you have this Globy, which is this dimensional embedding matrix that Stanford has in their website. So maybe you can use these word embeddings. But again, right, this is something you can do now, and you can customize, so to speak. And then after these word embeddings, we see here that basically we have first the words that are one hot vectors, then we have the word embeddings, and then we need recurrent neural networks. So we need a sequence to sequence model, right? And first RNNs So we started with RNNs, right? So the idea was to learn contextual word representations, right? And then you have a final layer. For example, it is a softmax layer that actually tells you, so the next word is books, laptops, eyes, whatever. So RNNs weren't very some sort of efficient, and Hochreiter and Schmidt-Huber invented long short-term memory networks, which is this complicated structure that was really well for language, right? That some sort of solved some of the problems of the RNNs, right? Of vanishing gradient and so on and so forth. And then it happened two things, right? So in 2019, so in addition, so transformers or BERT in October 2018. So we're going to be using BERT in our research, in our paper. So so BERT was launched in October 2018. It has 3.3 billion words, right? And it was trained using transformers, right? So transformers are arguably the best some sort of sequence to sequence, so to speak, or neural network architecture to deal with language problems, right? It can deal very efficiently with extremely large data sets, right? And so there are two main characterizations of these models. Again, first, the size, right, of the training set. You need a lot of text to make sense of it. And second, you need lots of parameters, right? Because transformers, or the transformers that are being more useful, need lots of parameters, so to speak, right? So, and that was done using these architectures. So Vashwani et al. In 2017, some sort of published one of the papers that has had the biggest impact in machine learning, right? And with attention is all what you need, and they some sort of introduced transformers, which is this multi-head attention, this feed-forwards, adding a normalization, and so on and so forth, right? So transformers are incredibly useful, right, to deal with language problems, okay? And then in 2018, Deflin, Chang, Li, and Tutanova launched BERT, which is a bidirectional encoder representation for transformers, right? And after that, so I'm not going to get into these details. You can obviously read that in our paper. But let's say the next large model was GPT-3, which was even a larger model than BERT with 175 million parameters, right? And so on and so forth, right? And GPT-3, it's well, one of state-of-the-art model. But what we're going to do, what we did, was to use a BERT model, right? So this is a paper we published in November 2021, and we call this model financial embedding analysis of sentiment. With my co-authors were Asier Gutierrez Fandino from the Barcelona Supercomputing Center, Jordi Armengol-Estapé, and Peter Colm from Courant. So the idea was, can we train efficiently a BERT-like model using transformers to deal with sentiment, right? So I said before, so typically sentiment, in the literature, you see lots of frequency methods, Luren and McDonald, positive and negative, and so on and so forth. There's another option, which is you have domain expert annotations. So you have humans actually saying, okay, this is a +1. This news is a +1. This news that says, I don't know, company had a drop in revenues of 21%. So this is a -0.97, right? If you use +1, -1 scale, right? So obviously, one caveat of using deep learning models is that they have to learn, right? So sentiment is not something that we can directly observe, right? So we have to measure it, right? And we either use frequency, or we have annotate humans that annotate a data set, right? And then we can use deep learning models, right, to just learn some sort of a model on how humans will interpret So Apple revenues were up 10%, and so on and so forth. So there's a lot of challenges, right? I won't get into the details, right? But so it's very contextual. References are important. It's oftentimes imbalanced. It's time dependent. Ironies and so on are difficult. You also need to deal with images and tables in the text, and impact is difficult to measure. So by no means, so sentiment is something, sometimes you have the impression in the market that people think that sentiment is just something really very easy to compute. It's not actually, right? But it's very useful because sentiment can be used obviously then to as a factor, for example, in your factor model, as a risk management tool. So something happened to a company in China, right? And so one of the some sort of selling arguments of these models, it's obviously you can do that much faster than humans. You can use that with different some sort of languages, right? And so on. Okay, so this is, so we used, as I said before, a Ravenpack dataset. Ravenpack dataset is a dataset that contains news, right? And they have annotated for every new what is some sort of sentiment score. Okay, and we see here this is a very large dataset. Okay, so we have in 6 months, you have some sort of 2 million, more than 2 million news. In 1 year, almost 5. In 2 years, 12 million, right? Well, is this a lot of news, right? As I said before, this might seem that it's a lot, right? There is a very large data set, and computer scientists and people will say, okay, this is a very robust data set, right? Because you have a lot of data, right? So actually, right, language problems are not that easy as we pick a lot of data, because maybe, and we'll see that in my conclusions, right, sometimes things have never happened, right, so to speak, right? Maybe in this 1 year, in these 5 million instances of news, maybe nobody talked about a bankruptcy. Maybe nobody talked about so we don't have to take for granted the fact that data sets are large, right? So maybe not everything that we needed to understand a new event was in the old data set. So that's obviously a limitation to this model. So I disagree with people that says, all right, these models are extremely large, right? So, okay. So this model is extremely large, obviously in terms of parameters. So these seem to be needed, right? But at the same time, data sets are very large, but maybe not, you don't have everything you need. Anyway, so the data set is pretty good, right? So you have low imbalance, you have means and max, you have nice boxes when we look at the score distributions, right? So we can say that a quantitative analysis of this 2 year, 1 year, 6 months and test set is some sort of, you see a nice distribution of the scores, right? Again, they have been previously annotated. When we look at the company distribution, you can see that in the paper. We also see a good behavior, right? And it follows a power law. So now, what did we do? So the idea, instead of using BERT model, right, so was to combine and use a sentence BERT model. Okay, so instead again of using word embeddings, the idea is to use sentence embeddings. So the fact that at the beginning, right, the words were used as a unit for the embeddings, that doesn't mean that you can't try with sentence embeddings. So that's what we did. We modified the sentence BERT traditional model. Okay, and you'll see in the paper, and we also offer the code, right? the use of sentence BERT. So, and we tried this in two steps. In one step, we froze the model. So sentence BERT was used as a feature, right? And then an unfrozen version of sentence BERT, which means that basically you can train also the sentences. You can use some sort of the pre-trained sentence BERT, but you can also train, right? How does this compare with BERT and bidirectional LSTM? So bidirectional LSTM, so LSTMs that read left and right and left are also incredibly useful, right? So here we can see that the model, right, in this first iteration in which we froze sentence BERT already gives a very low, this is the RMSE, so we're doing a regression here because sentiments is a number, right? So here this is the RMSE, which is pretty low, right? So the model is getting it, right? In 6 months and 2 years and 1 year, right? So model performs well compared to other BERT, so the vanilla BERT and bilinear LSTMs, which also do a good job, but you see the BERT, it has a quite high RMSE. So the standard, so to speak, so the model that was more popular or is more popular was FinBERT, right, by Dogu, Tarachi, and collaborators, right? So we unfroze a sentence BERT. So we actually train sentence BERT, and then we use that. And then we see that the model is also better performing, at least in 6 months. In 1 year, it's slightly worse. In 2 years, is better, right? So we could say that. Again, we think it's an interesting idea to shift from word embeddings to sentence embeddings. So model seems to be a little bit better. By the way, you can see in the paper that we haven't trained FinEAS on, we haven't pre-trained the model on our financial corpus, right? Which might give some sort of additional enhancement. FinBERT has been pre-trained using finance text, so to speak. Okay, so let me say something else before concluding and passing the to Matthew. So the RMSE that we see in the model is low. There's another one. The more the historical data, the better, right? So you can see, you can try. So you can go to the model and say and ask questions. So for example, default probability of default of Amazon is rising or it's lowering, right? And you might think that this is a very natural thing for the model to understand that this is positive or negative. But again, right, sometimes some of these sentences have not been seen in the data set, even if you have read for 2 years, right? So the idea is you need to read even more, right, than just 2 years. Think about a CFA that it's only trained by reading news in 2 years, right? Or something like that. So this is obviously not enough, okay, in our view. So let me mention quickly before concluding, right? So what does a language model know? So what FinEAS knows, what GPT-3 knows, what BERT knows, right? So we can see that predictions generally make sense. So they statistically make sense. Oftentimes they are factually not correct, right? And this is and there are several sources of risk, so to speak. Obviously, one is unseen facts. So the model has never read about probability of default, doesn't know how to interpret, right? There's some people that says then these models obviously pay a lot of attention to the verbs in the sentence. Of course, right? Verbs are very important in a sentence. When you lack precision on the nouns and so on and so forth, right? So unseen facts, rare facts, and model sensitivity, right? Maybe your model it's not interpreting correctly that X was made in Y instead of X was created in Y, right? So if we want some sort of infuse knowledge, right, to these language models, right, as you might want to make sure that the model is able to interpret well words like bankruptcy, like probability of default, and some words that might be rare, right, in your data set, right? You have several receipts, right, like added pre-trained entity embeddings using external memories with keys and values, modify the training data, right? So if you want to make sure that the model knows what bankruptcy is, maybe you need to give it examples, right, and so on and so forth, right? So, and this is incredibly important. Again, right, it's very important what the model has actually read, right, and what actually the model knows. So that was so this is in a nutshell, right, actually the results of our paper. So if you're interested, you can find it on arXiv, and you know, you have the code available. We can't actually share the data set because of limitations, right? Obviously Ravenpack is the owner and so on and so forth, but you can actually try the model using your data set and see how it works. Okay, so this is, yeah. Okay, so maybe, yeah, that was quick, but I think that in the interest of having some sort of dynamics, so we have now with us Matthew Dixon, who's going to talk us about generative reinforcement learning for goal-based wealth management. So thank you for being here, Matthew.
Thank you very much, and thanks for a very interesting talk. Hopefully you can see my screen.
Yes, we do, yeah.
Great, and you can all hear me okay?
Yeah.
Great. So this is, we're going to switch gears slightly from supervised learning or deep learning to the topic of reinforcement learning. Of course, the difference being with reinforcement learning, we have the additional feedback loop. And the additional caveat here is that instead of taking what would be considered the standard approach now of using deep reinforcement learning or deep Q learning, we're actually going to exploit the property that financial data is generally very noisy, and we're going to put the focus more on noise regularization, so noise suppression. And we're also going to develop a technique and introduce one here, which is extremely fast. Rather than taking minutes or possibly even hours to train a deep network and then embed that in a reinforcement learning algorithm such as Q-learning, the generative reinforcement learning is extremely fast. It's using what's called a linear quadratic regulator, which provides the ability to train and optimize a wealth management problem with several thousand instruments in the portfolio in the matter of minutes. So it's extremely scalable, and that's one of the main benefits here that we're going to be pursuing. The paper itself is available it was published in Risk last year, and there's also a Python notebook here, and the data is accessible as a S&P 500 time series with 100 stocks in the portfolio. So before I go any further, why is wealth management important, and why should we care about it as one of the main application areas of machine learning? It hasn't got as much coverage as, say, trading or other areas like investment management. It's actually a very prominent and rapidly growing area. You may have heard of what are called robo-advisors. But the main idea is to provide financial investment management solutions to pretty much anyone, not just high net worth individuals, but anyone who's worked and has saved and has a pension plan. And so it can cover all sorts of areas like tax planning or tax optimization, estate planning if you own property, and so on, as well as, of course, your investment portfolio and your retirement planning. How much should you spend? How much should you save? Should you send your children to an expensive college, et cetera, et cetera? These are all part of what is becoming a very sophisticated application area for machine learning, which is much more advanced than, say, the mean variance Markowitz type investment management problems. It's not just a portfolio problem. We're trying to optimize for spending and allocation and many other variables. So our goal here is to manage wealth for a particular, in particular, a portfolio should match a client's financial goal. And we're going to apply a generative reinforcement learning approach. I'll say what that is in a moment, in the context of robo-advisory. And so robo-advisory, of course, is a very broad area. It's still very much in its infancy, even though we've heard a lot about it. It's really just scratching the surface so far of what is possible. And so the main idea of robo-advisory is you have a certain time horizon for saving and for spending. You have a set of financial goals. Those could be a certain dollar amount when you retire. They could be, for example, a certain monthly income when you retire, or it could be an amount that you pay in per month as a percentage deduction of your, or dollar deduction of your income statement. And you also have a risk tolerance, which you may or may not know. And that's fine because we're actually going to imitate a human in this talk. Although I will say that we're going to be introducing quite a bit of math here, as the main sort of ideas are quite mathematical. And against that, the backdrop, you've got asset class performance as being an uncertainty. And there could be hundreds, possibly thousands of those assets. So it's a very high dimensional problem, which could not be solved realistically by other methods without making drastic simplifications in the properties, for example, of the asset returns, like the Gaussian. That's been historically the sort of classical approach. We're not going to do that. We're going to use the full data distribution. There's no reason why we have to restrict ourselves to modeling assumptions. And of course, there's market volatility, and there's different regimes and so on. And we know, as a stylized fact across, it's a fairly broad statement, but I think it's fairly accurate that financial data is noisy. And you're always in this scenario where as soon as there's a signal that every trading firm has, it sort of eats away at the returns as other firms capitalize on the profits. And so it's a dynamic problem. It's almost like a merging cats or morphing cats and dogs kind of problem. Finance is always moving. It's not image recognition. And so it's a much harder problem in many sense because you have a lot of noise and what you're trying to sort of model is always changing by virtue of the non-stationarity of financial data. So we're going to look at formulating the problem for reinforcement learning in the context or in the setup of a high-dimensional stochastic optimal control problem. And as I mentioned, the key input here, or the key sort of idea, is to introduce an entropy regularized reinforcement learning in a model-free setting. And as I said, that's going to be very important for trying to increase the noise and suppress, or increase the signal and suppress the noise. And we also have a very generic setup where we can have anything we want. We can have market friction effects, trading costs, trading impact. We can build that all into a general portfolio model, which would be impossible to solve otherwise. And we're also going to work with convex objective functions, so we actually have a global minimum. We're not just going to just hope for the best, and each time we run it, get a completely different answer, which can happen with deep learning or deep reinforcement learning, because it's not a global optimizer. There's no global optima. And so we have designed the problem so that you will get a global minimum. And that makes a lot of sense when you run the application. And if you, for example, we're using neural networks, you'd have to initialize the weights and you get slightly different answers depending on how you initialize the weights. And that can be unsatisfactory. So there are reasons to think beyond deep Q learning. And in fact, we'll show that you can get some very satisfactory results. So I don't have time to go into all the details because those are in the paper. But the general setup is we've got a universe of n assets. These are stocks in our case. And we're going to denote prices here, a little P of T. These are our market prices. We'll use end of day adjusted prices. And also we are always trying to determine how much of our wealth to keep in a risk-free bank account versus allocate that to across the stocks, across the N assets. And we'll denote the dollar amount of the allocation in each of the individual assets as X of T. This is not a percentage amount. This is not a fractional amount. This is a dollar amount. And that makes a big difference in the formulation of the problem, and it makes it actually convex with respect to the control, which is going to be the trades itself. So we're trying to determine what trades to make, how to optimize the trading. So we run this, it will trade for us, it will take account of potential trading impact. As you make a trade, it moves the market. If you're trading in a thin market, for example, or it's a big trade, it also accounts for fees, and also it clearly just uses the data. It doesn't have a simulated model of the underlying. Okay, so we're going to be focusing on an application which is called a defined contribution retirement plan, and it involves, without going into too much detail, combining portfolio allocation with consumption and target dated funds. So consumption is consuming, or if it's negative, injecting or investing cash into the portfolio to sort of increase the wealth level if it's not going to meet a certain target. And this is, in the simplest setup, this is known as the Merton consumption problem, but that has very restrictive modeling assumptions, which we do not have in this setup. For example, that is assuming Gaussian returns, and it can't handle things like trading fees and trading impacts, or at least trading impact. And so here we have a target, which is the difference between the growth of the portfolio post a trade. This is our dollar amount invested in the portfolio. This is our risk-free, this is the growth rate of the portfolio. So it's growing over a period. The portfolio is not self-financing because we're injecting, consuming cash. And if we meet a certain target or we're above it, P hat of T, then we do not have a penalty term. On the other hand, if we fall below this target at the next time period, then, or it could be a terminal time period, like a terminal, in the special case, a terminal penalty, then we will have a penalty term. So we have a consumption term here. We have a penalty for not meeting a target or being below the target. And we also have trading fees here baked in as a quadratic expression here, quadratic form, where omega here is the diagonal with the trading fees on the diagonal. Now, so that's what we're trying to optimize. And then we can pick a very simple choice for the target itself. It's dynamic. So we can write it in terms of some benchmark, like the S&P 500 index, and then some additional growth or fixed rate here. So that's slightly different from the benchmark. And these are two parameters here which we're going to build in because we don't know what they are exactly. And so we're going to try and build that in into the optimization process itself, so that we have a sort of a target dated fund that's always able to reach a certain target, and so that's based on obviously the performance of the historical data, how to set that level. And we're going to set up the problem so that we have asset returns, and we're going to write all of these down in terms of rewards, because remember, in reinforcement learning, you need to define three things. You need to define your state space. In this case, our state space is going to be our stock returns. And also, it's going to be the positions, the dollar positions in the assets themselves. The actions, the control, are going to be the trades, and there's a feedback not onto the trade prices or the market returns, but onto the trade allocations, the positions, the dollar values. So when you trade, you change the position of the portfolio, and hence there's the Markov decision process with a feedback loop. If you didn't have that feedback loop, you could do supervised learning, but we do reinforcement learning because there's feedback. The actions change the state space, and those are observable variables. So we have a fully observable state space, we have actions, which are the positions in the portfolio plus consumption, how much to consume in each period or inject. And the rewards are defined based on the target we already had before, and we can expand out that expression that we saw before here, just write it out, expand it a little bit more. And also we can make sure that this is differentiable by introducing some soft version of this function here, so that essentially we have a smooth type of a smooth approximation to this ReLU function. It's just a max here, so it's a ReLU. Okay, we're not doing neural networks, just because I said ReLU, it's just we're doing, there's nothing to do with neural networks in this talk. So we end up with a problem with 4 parameters, which is kind of nice. When you're used to working with deep networks and having to find millions of parameters, we now just have 4. And you could say, well, you know, how can that work with only 4 parameters? But we put a lot of thought into designing the rewards so that it actually meets our objective. And we are not making any assumptions about the underlying. And we have to introduce one more parameter in a moment, which we're going to talk about. But in the interest of time, I'm just going to move forward a little bit and say that what we're going to do is our goal, or the goal of the exercise of reinforcement learning, is to find a stochastic policy. So this is a conditional distribution given your state space variable, in this case, partial state space, it's just the assets. What are the allocations, the trades that you have to take, the actions, and this will give you a distribution, a conditional distribution, so that every action is essentially given by probability. It's no different to a self-driving car. You know, should you turn left, should you turn right, given that there's, you know, a ball that's run out in front of the car, there'll be a certain probability of turning left, a certain probability of turning right. That's your policy. And so here we're learning a conditional probability distribution. It's a continuous random variable, conditional random variable, and so we are going to actually model the evolution of the stochastic policy directly as a random variable. And so we're going to call this a generative model because we're taking into account the full distribution. We're not just looking at the expected value. For example, that's what you do in deep learning. You just look at the expected, or the conditional expectation. You try to, to maximize that. If you're trying to do least squares type optimization, here we're keeping the full distribution, not just the conditional expectation. And so we can write now our problem as a Markov decision process. There's our time value of money, gamma there, which is, you can think of this like a growth rate in your interest-free bank account, time value of money. There are rewards that we've already defined. And then we're going to write down an evolution of our stochastic policy based on the trajectory of the state space. So this is what's known as a Markov decision process. This is a transition probability that we have to find. We don't know it. We have to find it, and we have to infer it. And this will give us a quantity here, which is the evolved stochastic policy. There's the starting point, and then we subsequently update it over all time horizons. And this has to have always have the property that if you were to integrate it, it sums to 1 because it's a conditional probability. Now, this is important because once we have this, we can then just pick our reference policy. We're not saying anything here about the stock returns, merely making an assumption, an initial starting point for the distribution of the allocation. So we might start with a particular distribution of that allocation, and then we're going to evolve it, and we're going to assume that there's a linear dependency on the actions and the state space. And that enables us to solve the problem very quickly. You could replace this with a neural network here so that you have some higher order approximation, but then you get into difficulties with losing the convexity, and that is a heavy price to pay for what may be really a secondary impact on that action state regression. So we're going to assume that, And at that point, we can then write down a Bellman optimality equation, if you're familiar with dynamic programming. And then we can write down, skipping a lot of math here, we end up writing down an important quantity here, which is known as the information cost of a learned policy. It's a sort of an idea that comes from statistical mechanics. You write down your initial distribution, and then you write down what the current distribution is of your allocation, and this is known as your information cost. And once you have the information cost, you take the expectation of that, and you have your what's known as KL divergence, Kullback-Leibler divergence, which is a measure of information. This is the foundational ideas behind machine learning is information theory. And so we're characterizing everything here in an information theoretic setup, which is what you do when you use log likelihoods in neural networks, except we've now expanded that and we've got a slightly more general setup that accounts for the information cost. So we end up now penalizing this information cost in addition to our usual state value function. And we have an additional parameter here which controls how much to suppress the noise. And in financial data, as I mentioned before, it's really very optimistic to treat your data like it's an image processing problem when it is so noisy. I mean, think about all the vagaries of people when they're trading. There's an enormous amount of noise in the market. And so our goal here is to find how much tune this parameter beta to suppress that noise and do it in a way that penalizes when there is high information cost associated with the state variable. Okay, so from there on, it's just some math to reconvert it. And this is where the concept of G-learning comes from, is that we, instead of working with Q-learning, which is a state action variable, we now have this free energy version or regularized version of the Q function, which we're calling the G function. Okay, and so the G function is designed for noisy data. The Q function is not. And so that's the big shift here in thinking. You could do deep G learning if you want to, but we're just going to do, as I said, a simpler setup. And so this is a really important idea coming from statistical physics and statistical mechanics, which of course is very used to this idea of having to deal with problems of noise. And then we can set our terminal conditions. We start at the back, at the very final period, and then we work backwards, and we start to run the data through the model, and we look at various different state action trajectories, which we draw from the data, and then we simulate the different actions. And we do that, 100,000 times or 10,000 times, and it can be done in parallel because it's embarrassingly parallel. And you end up essentially simulating the rewards, and at that point, you're trying to take the expectation over the state space, over the simulations of different paths, and determine what the optimal set of what the optimal policy is. So the details here, of course, are rather involved, and I'm not going to go into them. And it's certainly, I'm not going to sell it as a black box because you can run the code, but it's with any technique that requires some thinking, it's not going to be a black box. It's going to require more math, and so there are many advantages to using this approach. I said, what you gain by using math is massive speedups because you've now exploited the properties in the data. You've set things up to be convex. You've figured out what you need to do with the data, in this case, the noise. And the gain you get is avoiding a black box approach, where you just end up with massive numbers of parameters and a huge amount of over computation that slows everything down. And you end up then just chasing tooling and so on to get the speed up. Or you can be lean, you can think about the problem and formulate it in a way that makes sense. So I would argue that's what we've done. And so, but it remains to be seen how it compares with, say, deep Q learning in terms of the performance. In terms of speed, it's a big 100x gain over deep Q learning. And we're going to use this iterative linear quadratic regulator, apply that to optimize. That's the main optimization algorithm that we're going to use. Apply that to our G-learning function itself, the objective function that we're trying to optimize, and then simulate these different trajectories, update that policy in this nice closed form way, so it stays Gaussian all the time. We're just updating it, evolving that Gaussian, shrinking and collapsing it as we need to, maybe shifting the mean as well. And that's going to determine what our allocation is. So we have, that's reinforcement learning. I just have a few more minutes here before I get into the results. We can also imitate the human. So we can imitate an investment manager where we don't know what the rewards are. We don't know what their objective is. And instead, what we're trying to do is learn from their actions. And so as we observe somebody trying to manage wealth, where it's a wealth manager, we can imitate them. And so what we do here is we imitate, using a log likelihood function, a human who, or indeed another robo-advisor, where we know the actions that they take. We know the use, we know the trades that they make, we just don't know the reward function. And we're trying to essentially learn a utility function from another agent. And that's actually a really powerful idea if you think about it, because you could start to understand what wealth managers are really trying to optimize. You could find a rogue wealth manager who's trying to optimize for their own self-gain. For example, that they have a commission. Or you could find someone who's not investing in a sustainable way, ESG compliance. This is the very tip of the iceberg, I think, and it's an exciting time to be thinking about imitating humans. So we use inverse reinforcement learning. We actually going to learn the G-learner itself, see if we can reproduce the parameters, and that takes a little bit more time computationally, but we did it just to as sort of out of further curiosity. So our setup, we've got a few minutes remaining. Our setup is we're going to use a factor model, a CAPM type model, in fact, to predict the expected returns. That's a standard model that's used across the industry. And then we're going to provide that to the G-learner, and it's going to then manage the portfolio for us, manage the wealth, and determine what the optimal consumption is. So that's one model that we're going to use. It's an oracle mechanism predicting expected returns, which is CAPM-like. There's your average or mean returns. There's your AIFI asset returns over so this is expected excess returns. These are your actual returns, and then there's some noise term, and the C here determines essentially, it's a chosen value, but essentially determines how much information you have, and it's typically very low. The R-squareds for these kind of models are very, very low. And that's why prediction is extremely difficult in finance. If it was easy, everyone would be rich. So the second model is OLS regression, and we're just going to progress the asset returns or the mean asset returns onto past excess returns rather than doing some sort of CAPM type model on the market. Okay, so the period is 2 years, and we're going to look at monthly periods over that time period, sorry, quarterly periods, and we're going to choose to have 100 instruments, 99 stocks, and so with model 1, which is a sort of CAPM type model as our oracle, we have the performance of the model here. These are our quarterly risky returns, just for one of the assets. So we can just see here what it looks like. These are our portfolio returns, and so we have the performance of the portfolio if it just had equally weighted instruments. So if you sort of essentially didn't use any information for the market, you just picked equal weights, this is the performance you would get. If you now use this sort of weak oracle signal that we didn't tune, this is the G-learning algorithm. So it's taking that oracle and it's trying to optimize the positions as much as it can, and tries to, again, suppress the noise as much as it can as it's trying to learn what the optimal policy is for trading. And we also get the consumption results here for how much to consume over each period, either as an investment in negative value or a positive value, meaning you're consuming. And GIL is the inverse reinforcement learning agent. It's imitating the G-learner. So it's imitating the robo-advisor, if you will. And that's able to learn the behavior of the G-learning algorithm as well, with just a few parameters there, and also match the consumption. And we can change the oracle to see how sensitive the model is to the oracle. So you could choose a different model for predicting returns. You could have a nice big factor model, for example. Again, very similar results, not exactly the same, but it definitely pays to use G-learning as a reinforcement learning tool. It's very fast, as I mentioned, and it has the advantage here of increasing the Sharpe ratios. These are shown in the parentheses there. And we've done this on a fairly short time horizon without developing a much more sophisticated oracle. But we have this sort of benchmark here, which is just an equally weighted portfolio. You could do mean variance as well as a benchmark. So we've introduced a generative framework. This is my last slide. I'm wrapping up here. This is well suited to noisy data. It scares some people because it's got math in it. On the other hand, the concepts are very well worn. It's just a Markov decision process, and we're just building into it ideas which have been around 100 years in sort of statistical mechanics. It's not for everyone, but it's definitely has the advantage of being very fast and honing in on the exploiting the fact that we have a convexity, and therefore we get a unique optimum. And we don't have to worry about rerunning this and getting different answers, which is the real bane of using deep learning tools for problems like this. And we also have performance results on the S&P 500 data over a 2-year period demonstrating the G-learner, and you can run those results on that data. And we also have some results showing how to mimic an agent. In this case, we pick the agent to be the G-learner itself and show that we can imitate it and reproduce some of the parameters. And that's an exciting direction for ability to imitate agents in the market, whether they be wealth managers, and try to learn from humans and then do better than them. All right, so I'll finish there, and thanks for your time.
Thank you, Matt. Miquel, do you have your chat windows open? I'm not seeing anything that's been posted publicly, but you might have received private messages.
No, I haven't, but obviously that's a good opportunity for the participants to ask questions.
Indeed, we've got somebody asking if we can have the presentation slides. So I know Matt's already provided those. I'm guessing, Miquel, you're going to send them to me a little bit later.
Right,
and then
yes.
We'll have the recording and the slides distributed by tomorrow, we're hoping.
Any questions about the...
Can I ask a question? Crystal speaking here.
Yes, please. Yeah.
First of all, thank you for the 2 very nice presentations. I have a question to Matthew. Have you seen your model apply to fixed income world?
We have not. I mean, this is a model that is being, I can't say very much about how it's being used at Fidelity for confidentiality reasons. Obviously, the co-author is at Fidelity Investments, Igor Halperin. I believe that they also look at fixed income, but I think that would be an exciting area, but we haven't done that. I think that would be, a very interesting direction, especially if, those instruments are noisy, and so, and where there's a need for, scaling up to very large portfolios. This approach is very scalable across big portfolios.
Thank you.
We have a question about what is the generative aspect in the generative RL? DJ is asking.
Yeah. So generative just means it means that we're trying to model the full conditional distribution, as opposed to just in deep learning. What you're generally trying to do is find the optimal output given some input, which is a conditional expectation. You're not trying to find the optimal distribution of the output. In generative learning, you're learning the optimal distribution. And so our results are an entire distribution of the allocation across the stocks. It's not just a single number telling you how much to invest in each stock. It's an entire distribution telling you how, where you should center the most concentration, but also probabilistically how you might assign to other instruments. So it's it's a very standard technique. It's sometimes called Bayesian as well because you're working with a Bayesian setup. But the main goal is it's very useful for risk management because you've got the entire distribution. You've got a lot more information at your hands, and that's why there's a lot of interest in using this approach. It's also very easy to update it when you get new data, as opposed to having to retrain the entire model again. So it has a number of benefits. How sufficient was the alpha generated over the S&P 500? Well, we just looked at Sharpe ratios here, and we've used a very weak signal. We haven't used a more fully fledged factor model. So we were seeing Sharpe ratios with trading fees, could be as high as 1, which doesn't sound like a lot, but when you consider the case when you're using something like equally weighted portfolio, it's terrible. And so there's definitely a gain. And what we had to do mainly was develop a lot more sort of fundamental machinery to be able to do this. And we're hoping that the code can be used and run and tailored towards more financial performance studies, which look at more advanced signals or more advanced asset models, like factor models, for example, and try to really see how well those do against mean variance type optimization approaches or other approaches. So I mean, the alpha itself is we look at the Sharpe ratio and try to characterize that based on trading fees that we have which are based on the S&P 500 trading fees.
There's a question for there's an NLP question. Okay, Terry. Hi, Terry. He's asking how widely is RNNs being used for sentiment analysis. So, well, obviously, right, finance is a domain in which we obviously practitioners some sort of don't share, right, their models. But we have to say that two things. So first, everybody was at the beginning using frequency methods, which are very easy to compute, which are very easy to understand, and so on and so forth, right? But the issue about using BERT-like models or LSTM models is that they provide some sort of a lot of precision, right? On the drawbacks are obviously that you need annotated data, right? Except if you do something that is very straightforward, which is connecting, right, directly news to returns, right? So some people is some sort of bypassing, so to speak, sentiment in the sense we're going to connect news to returns instead of we're going to connect news to something, and then this something called sentiment or right, then I'm going to use it in a factor model, right? You see what I mean? So there are several ways, but obviously deep neural networks have the problem of you need annotated data. This is not easy to get, right? But frequency methods are very crude because you do not consider the sentence, right? And annotating is very expensive, so to speak. So you have here, right? And there are other options like trying generative models like GPT-3, for example, and then trying to see if this generative model, which Matthew defined, so instead of computing P of Y condition to X, you're computing P of X, right? And then you try to use this statistical distribution to do some tasks, right? And understand more of the data, create more data, right? So, so to create a pure generative language model like GPT-3 is something also interesting, right? But it's not clear that the model will be as knowledgeable as saying, oh, this is good, this is bad, but we haven't tried, right? To use, so to speak, an unsupervised model and then see if it learns, right? If this is positive or negative, right? Yeah, so this is, any other question? Yeah, The model not overfit. Okay, so that's a good question. Obviously, right, about overfitting, right? We know that model, right? So if we look at the results, if we look at the results 2 years, 1 year, 6 months, and then the test set, results are incredibly robust, right? But I would say something that we cannot be some sort of cheated just because the model approximated very well 6 months of data, right? Or 2 years of data, because something new could happen, right? And obviously the model can fail horribly, so to speak, right? So I would say that that you have to be very careful about what the model knows and doesn't know, right? And that brings us to the realm of domain experts should spend time with the language model to see if the language model actually knows some sort of relevant stuff that might occur in the future. This is not very quanti, actually, right? But again, you have to, that's why we think that the model has to be trained with many years of data, because actually, again, the model has to read and has to be aware of things like the financial crisis, defaults, bankruptcies, I don't know, for example, specific things that could happen to a sector, and so on and so forth. So that's why again, you have to train the model in your context, be very careful about the new things that might happen, but also test thoroughly, right? If the model is actually catching things that you think are interesting. As I shown in my presentation, so there are several ways to make sure that the model knows, right? You can actually show the model key values, you can actually show sentences, you can actually show to the model, right? Okay, so here's a problem. Yeah. And then obviously in terms of our model, it has to be, it remains to be seen to what extent training, right? The training FinEAS in a specific context, right? Financial context will deliver, right? Good results. But my assumption is that while it might not increase probably some spectacular results in the short term, the model is probably going to be more robust, as I said, if it sees more and it knows more of finance. It's like a CFA, right? So the CFA, to acquire his knowledge, it has to be reading all the CFA materials, seeing lots of stuff, and so on and so forth. Just reading 2 years of news, it's certainly not enough to understand financial markets, right? Yeah. Yeah, and then Pluricha is asking, how well could G-learning adapt to structural breaks?
Yeah, so that one, I think the short answer is probably not very well. But if you introduce a Gaussian mixture model instead of just having a Gaussian prior, then you could handle different regimes. And so that would be an interesting exercise, actually, is to have some sort of Gaussian mixture model and then update, mixture of distributions and learn the allocation as a dynamic variable. But that's, beyond the scope here. I think that's an interesting direction for sure, but we haven't done that. And then there's another question here by Terry. Hi, Terry. So a minimum amount of data needed to find optimal policy. This is actually a really good question as well, because another advantage of sort of being in a Bayesian framework is you need much less data. And in fact, there's only 4 or 5 parameters here to tune. You need very little data. And what does that mean when I say little? I mean, you don't need thousands or tens of thousands of observations. You are essentially just trying to expand or compress, contract or expand and shift the policy itself, and you already have sort of a starting point, as good as your starting point is. Obviously, if you choose a bad starting point, then then you're going to have the problem, which is sort of the downside of Bayesian. So I'm not going to put an exact number on it and say how many observations you need. I don't know, but I don't know if there's theory to even say what that is. But you can reduce the amount of data required, both. It's a twofold effect, both by using a Bayesian approach, where you're sort of kickstarting the model essentially with a prior, rather than starting from scratch. And additionally, there are very few parameters in the model, so and those parameters are economically interpretable as well. So there's pros and cons. Different tools for different problems. Obviously, deep learning is a very useful tool. Clearly, as Miguel has said, but in this context, it can be quite a lot of dead weight to be carrying it around on a reinforcement learning algorithm, especially if you only have quarterly data. You don't have very much history. It can be really difficult to train deep Q learning problems as well. So I'm glad you mentioned that question, because that's another problem, I think, with using deep Q learning if you don't have that long a period of history to look at.
Okay, we have a question from Kamer, or some sort of a terminology precision. He says, or she says, zero-shot models are not trained to predict an outcome. Yeah, so generative models are not trained to predict an outcome, but it's probably too optimistic to think that a model that hasn't been trained to the specific task is going to be zero-shot. Or so if we look at GPT-2 compared to GPT-3, GPT-2 was zero-shot, and then the guy said, okay, let's change and say few shots, right? And so on. So I don't know, right? It's hard to me to understand why the model would be as intelligent as saying this is going to be good or bad or just neutral, right? If it's a classification problem, but I haven't tried, right? I don't know, right? But that's again an interesting thing to look at. But I'm not sure that the unsupervised learning model would understand. But so you should ask GPT-3: is Apple revenues up a good thing or a bad thing for the stock, and see what it says, right? Maybe it surprises and says, oh, this tends to be good, right? But I think you have to try before using it in real life, obviously. But that's a very interesting question, right? Yeah. Yeah. The SME credit scoring, right? So just one precision about sentiment analysis. So obviously sentiment analysis, as I said, it requires data, so to speak. So SMEs will typically not have probably a lot of data, for example, lots of news and so on, right? But you might have data, right? Some sort of unstructured data. You might try to see if you have enough of a data set that gives you, the financials of an SME and some sort of a credit scoring. So you should train. But it's going to be a hard problem, right? Because you're not going to have a lot of data, right? So I guess, right? But yeah, but that's an interesting research question, right? Yeah. So maybe one last question, right? Matthew, have you gone through all the questions in your chat?
Yeah, I think so.
Yeah, I think I did that too, right? Finberg, like this. Sure. Yeah. Well, just reiterating on the comment that it's a long comment from Ale. I couldn't agree more in the sense that these models provide some sort of very high precision, right, on the test set, right? But language is also a non-stationary thing. Again, tomorrow we might We might have an event tomorrow that the model doesn't understand, that the model has never seen, that the model is not interpreting well, and you have a horrific failure, so to speak. So you have to always pay attention to, for example, to the novelty of the events that actually coming, and see if the model is actually knowing it, right? Yeah. So I think that obviously, right? Obviously, the performance in the test set is often overestimating, right? Just because we don't know about unknowns that might come in the future, and probably the first time that the model saw COVID, it needed a little bit of time, right, to understand, you know, what COVID means, if this is good or bad, and so on. You would say it's going to learn that quickly because the first articles are going to see, okay, are going to say, okay, COVID is going to have a huge negative impact on Apple revenues, right? You see what I mean? So you're going to the model is going to learn that this is a bad thing, right? Typically, right? But you have to be paying attention to all the holes, right? That could be, yeah. So neural nets cannot obviously again invent, you know, or understand probably something that they've never seen example, right? Maybe yes, they can extrapolate, but it's pretty hard problem, right? To think they're going to be able to, right, to make connections and so on. Yeah. Okay, so I think that we've covered all the questions. So yeah, thank you very much, everybody. Thanks, Matthew. Yeah, thanks, Ed, for hosting, and see you in the next webinar. Thank you very much.
Thanks, everyone. Thank you, Miguel.
Thank you, guys.